In this third problem, we see that we have a argon gas coming in to a turbine, and it's operating in a steady state mode from a pressure of 10 megapascals, 51 degrees Celsius, with a given mass flow rate of 1 kilogram per second. And it expands adiabatically to 4 megapascals, minus 35 degrees Celsius, with no change of kinetic energy or potential energy. We are being asked to use the real gas model, this time the Nelson-Obert charts, and to determine the work developed as well as the entropy generated. And then the what if scenario is to see how the answer would change if one had selected the ideal gas model. And so for this particular problem, we then go into our test apps and we recognize that it's once again a flowing open system. And so we select that. Our gas model in question will be a real gas. And we're then ready to go into the HTML test app. Our mode of calculating the real gas behavior is the Nelson-Obert charts, and we are selecting argon as our gas. So with this in mind, we are told a number of things. The first thing is that the flow rate is 1 1 kilogram per second. We recognize that it is argon, which has a molecular weight of about 40. Our incoming pressure is 10 megapascals. And our incoming temperature is in Celsius. It's 51 degrees Celsius. And so that is our incoming condition. We have no kinetic or potential energy, so these two terms are zero. What we can observe immediately for this particular gas is that the reduced pressure is about 2, and the reduced temperature is about 2.1. And again, all that means is that at this temperature, the critical temperature is more than half of this, or so. The critical temperature is probably about 150 Kelvin for argon to have a corresponding dome. So that's our state 1. Our state 2 is an expansion to 4 megapascals. And we see a corresponding drop in the reduced pressure, minus 33 C and minus 35 C, and that corresponds also to a lowering in the reduced temperature, and we have the same m dot as before. Now, for these two states, if we look at the first state, we see that we're about 3.5% below the ideal gas behavior. Our compressibility factor is about 0.96. Here's our departure value as well as our entropy departure value. Our state 2 is about 6% below the ideal gas behavior at a compressibility of about 94. And so we're going to see a 4 or 5% decrease in the work developed because of it not being the same as an ideal gas. And so we then go to our device panel. We have our incoming and our outgoing state. The problem said that it was entering the turbine at steady state, expanding adiabatically, and so that implies that there is no heat transfer. And then upon that, we then see that our energy equation allows us to determine that the external work, or the work that was developed by that expansion, is a positive 4258. and we also see that the S dot gen, which is what they asked us to find, is 0.0312 kilowatts per kilogram. And so this is then the answer to this particular problem. If I were to redo the problem, but assume an ideal gas behavior for the argon, one would get a work of about 44.7 and an entropy change or an entropy generation of about 0.0302. So about 3% less entropy being generated and a little bit more work being generated. So that is problem number 3.